The next thing we want to observe about the matrix A is that A has a pivot in every row. That's the next big observation. A has a pivot in every row. A has a pivot in every row. This tells us something about the columns of the matrix A. The matrix has the pivots. This tells us something about the columns of A. Here's what it tells us about the columns of A. We're going to introduce a new concept. This tells us that the columns of A span R3. The columns of A span R3. New word. Span is something a set of vectors can do. So it's a verb that goes with a set of vectors. Notice that when we write the columns of A, we were talking about a set of vectors. I think it was green before. No, I can't remember. Remember, A is a matrix. The columns of A is a set of vectors. Span is something that a set of vectors can do. So what does this mean? What does it mean that the columns of A span R3? And I'm going to follow this up in the same format that we did with the pivot in the column pivots. And the next thing I talked about was, what do the pivots have to do with the equation? So if the matrix A has a pivot in every row, then the equation AX equals B is consistent for all B in R3. And that's what it means to span. The equation AX equals B is consistent for all B in R3. This is what it means for a set of vectors to span a space. That's why earlier when you asked the question, what makes AX equal B consistent? I'm like, oh man, hang on. Because I knew it was going to be consistent, but I had to leave it up in the air. I had to say if, because even though in this particular example I knew. But AX equals B is consistent for all B in R3 because the columns of A span R3 because A has a pivot in every row. Another way to say this is that every B in R3 is a linear combination of the columns of A. So we can use it in terms of combinations as well. Oops. Let's say every. When you want to make something a linear combination, it's a linear combination of a set of vectors. So it's not a linear combination of A, that doesn't make any sense. A linear combination of the columns of A, that's how we say it. I realize that a lot of this class can be done in the Drake format, so that's what's going in my mind. I'm turned away from linear combination of A because that doesn't make any sense. Then I'm smiling and pointing that linear combination of the columns of A, because the columns of A is what makes it a set of vectors. Let's talk about why AX equals B is consistent for all B in R3 if A has a pivot in every row. The short answer, the one that you need to carry forward for justification, is that we've used up all the pivots in the coefficient matrix. If A has a pivot in every row, then the augmented matrix A augmented B could not have a pivot in the rightmost column, because there's no more pivots. We've used them all in all the rows of A. The augmented matrix A, B could not have a pivot in the rightmost column because A has a pivot in every row. There's nowhere else to put a pivot. No matter what I put on as the fifth column, no matter what shows up in the fifth column, there will not be a pivot in that column. I've used up all my pivots in the rows of A. So all these statements are equivalent, but that does not mean that all these statements can be used to justify each other. So if I ask you, do the columns of A span R3? You can't say yes because AX equals B is consistent for all B in R3, because now we're going in circles. The question is, how do you know that the columns of A span R3? And your justification needs to come down to the thing that you observe. And the thing that you observe is a pivot in every row. So if I ask, do the columns of A span R3? Yes, because A has a pivot in every row. Is the equation AX equal B consistent for all B in R3? Yes, because A has a pivot in every row. If I ask, is the equation AX equal B consistent for all B in R3? And you say, yes, because the columns of A span R3, you're just throwing the definition of span back at me, and that's not what I'm asking for. How do you know that the columns of A span R3? And that's A has a pivot in every row. You never need to pull out the augmented matrix. This is just so that you can understand why this is the case. So this is how we think about it. We've used up all the pivots in the coefficient matrix. There will not be a pivot in the rightmost column of the augmented matrix. Remember, never say rightmost column without saying augmented matrix. Let's look at another example of a matrix where different things happen. Page 4 already? Burning through the knot paper. So I'm going to say, here's B equals, and clearly I'm not going to be writing an augmented matrix. This is just a local rule. I never name an augmented matrix with just a single letter. So let's look at this matrix. 1, 2, -1, 0, and then 0, 1, -3, 3, and then -2, -3, -1, 5. So I got 4 rows and 3 columns. Now, before we actually make any calculations, let me ask you this. Do the columns of B span R4? How do we know right away?
No.
Why is that? No is correct.
Because you can't have a pivot in every row.
We cannot have a pivot in every row. Perfect. There are 4 rows and only 3 columns, so it's not possible to have a pivot in every row. So the columns of B do not span R4. Notice that the columns of B come from R4, and not R3. So here's another fun thing that we get to learn about our calculators and the ridiculous limitations they place that we get from our calculators. So I want, oops, no, that's not it. Matrix alpha. There we go. So I'm going to put this matrix in. So matrix row, and I'm going to put in 1, 0, -2, close the row, open the next row, 2, 1, -3, close the row, open the next one, -1, -3, or -1, close the row, open the 4th row, 0, 3, 5. Close the row, close the matrix, close the command, and get an error.
I guess you forgot the comma after 0 for the first row.
Error, invalid dimension. This is false. I don't know where TI-84 gets this, where TI-84 gets their programmers. It's perfectly possible to find the reduced or echelon form of this friggin' matrix. I don't know why it's invalid dimension. But whatever algorithm that Texas Instruments uses to find the reduced or echelon form of their matrices, it won't do it if there are more rows than there are columns. I've been wanting to ask my computer programming literate friends to figure out why this is, but it's not enough of an issue for me that I really actually pursue that. So we can't do, we can't find the reduced echelon form if on our TI-84 if we have more rows than columns. This does not mean we get to bail. What we're going to do is drop in a column of zeros. And this is the only workaround that I know that gets us to what we want. But we're just going to ignore that column of zeros. I'm going to put in enough columns of zeros to square out the matrix, because Texas Instruments will reduce that. If someone knows how to make another way to make our calculators reduce these matrices, then please let me know in the comments. But I've turned comments off, so maybe that's why I don't know. But here's the reduced echelon form of this matrix: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. So we got a pivot in the first row, first column, second row, second column, third row, third column. These pivots were always there in the matrix. We just needed the reduced echelon form to find them. So here are some observations that we can make. B does not have a pivot in every row. That's what we can observe. B does not have a pivot in every row. We knew that this was going to happen. We knew that it could not have a pivot in every row. Here's what that tells us. The columns of B do not span R4. Note that the columns of B are in R4 because they have 4 entries. So whatever you build out of the columns of B, it's going to be in R4. They have 4 entries, so they're in R4. The columns of B do not span R4. The only thing we can build out of the columns of B is going to be in R4 because of the 4 entries. And there are some things in R4 that we cannot build. Let's talk about this in terms of equations. The equation Bx equal, this is why I wasn't using B, but that's okay. Bx equals B is inconsistent for some B in R4. This is the negation of consistent for all B in R4. One way to negate consistent for all B in R4 is to say inconsistent for some B in R4. We can't just negate the previous statement by saying not and then not changing the for all part. The opposite of consistent for all is inconsistent for some. So the equation Bx equals B is inconsistent for some B in R4 and consistent for others. The matrix equation will always be consistent for some of the vectors in R4 because the homogeneous equation is always consistent. You can never make an equation that's inconsistent for all B in R4. So some of the B in R4 are combinations of the vectors in the matrix the columns of B, but not all of them. Any questions? So it's possible to construct an augmented matrix that has a pivot in the rightmost column, but not necessary. It could be that for some choices of B in R4, we do not get a pivot in the rightmost column. Here's one thing that we notice about B. Note that B does have a pivot in every column. B has a pivot in every column. That's what we can observe. So that's going to be our justification for any conclusions that we make. We're either going to make row conclusions or column conclusions. B has a pivot in every column, so we could say that the columns of B are linearly independent. Linear independence goes with uniqueness of solutions. So if the equation Bx equals B is consistent, then the solution is unique. If the equation is consistent, then the solution is unique. So the connections that we're making, row goes with span, goes with existence of solutions. Columns goes with independence, goes with uniqueness of solutions. So when you go back to quiz linear combinations 3 and quiz linear combinations 4, I asked you to explain things. Your explanations need to be based on things that you observe. And all that you get to observe are the pivots. Those are the things that you observe. Everything else is a conclusion that you're drawing. So always look at your reduced echelon form through the pivots. Another important thing to note here is that we can't, there are certain things that we can claim based on the size of a matrix. Here, the matrix B could not possibly have a pivot in every row because there are more rows than there are columns. The matrix A from the previous example had a pivot in every row, but it could not possibly have a pivot in every column because there are more columns than rows. If I have a 3x3 matrix, we don't get to make those determinations until we're looking at the reduced echelon form. So if I have a 3x3 matrix, it could have a pivot in every row, but it might not. In particular, here's a 3x3 matrix that does not have a pivot in every row. But if there's more of one than the other, then we won't have to have pivots all the way across or all the way down. Any questions? All right, so those are the row things that we wanted to talk about. We had column questions and we had row questions. All of these conclusions are based on what we observe about the pivots. So let's pause the video here and talk about just a few more details that we want to get through.